All right, well, thank you everybody for coming. My name's Austin. This is Jakim. That's Heidi and Sarah. They're all civil engineering students here at the University of Umary, and our senior design project is the reconstruction of the South Washington corridor. So for those that are familiar, the north end of our project is basically where that elementary school is. Down to the south end is Burley Avenue, all on South Washington. So it's a pretty straight shot down in the river valley. Currently, there are two lanes, one going in each direction with a four-way stop at the south end at that Burley Avenue intersection. The main need for our project is that population in South Bismarck is growing rapidly, so they are needing to just expand the roadway a bit. So that's what our proposed roadway will be, is 3 lanes. It'll have 2 driving lanes and then a center lane to turn with. And then on the south end of the project, there will be a roundabout. Now, once you expand the roadways, it causes you to need an updated drainage system. So we went with a curb and gutter system. We had 3 main design considerations, which were the pavement design. We went through the asphalt thickness along with concrete thickness. And then we needed the drainage system, which we ultimately went with curb and gutter. And then we also did research studies into the life cycle assessment of both the cement and asphalt, and then the life cycle cost analysis. So starting off with our pavement design, our 3 main points where we had to gather the traffic data for our location, which primarily we needed to figure out how many heavy trucks will be going through the area. And then we also needed to get the soil borings so that we knew what type of soils will be below our road. And then we used both of them to calculate the pavement thicknesses for each concrete and asphalt. So starting with asphalt thicknesses here, you can see the left side is basically the strength of the soil beneath the roadway. And then the bottom is how many trucks will be going through on our roadway. And so then you just draw up from the bottom and then over from the left, and where they cross will be your depth of pavement. We about 5.5 inches. And so for constructability reasons, we rounded it up to 6 inches. And then for concrete thicknesses, it's a pretty similar calculation where it's on the left is still your strength of your soil beneath the pavement. And then the bottom on the far right is the amount of trucks going through along with like the reliability. And once again, it's once they meet up in the middle on that far right is where you get your pavement thicknesses. And in our case, we ended up with roughly 8.5 inches, which here is like what the final design would look like of the roadway. As you can see, the top is the asphalt design with the 6 inches of asphalt on an 18-inch base. And then the concrete design is 8.5 inches, 12 inches of base. We also were able to calculate the amount of fill we would need, which it's said to use 90% in the soil borings of that original in situ soil, because it's mostly a clayey soil, which isn't very good to build your roads on. And so then we needed the fill on the, which is the far 2 right sides on each the concrete end. And this all came together to be roughly 9,000 cubic yards.
So for the drainage design, what you see in this picture is pretty much where the roundabout is being added in. So there are grass waterways, drainage ditches on each side of the road. So since that the road is being expanded, the ditches will no longer be needed. So we pretty much came up with an idea to do. So what you see here is pretty what I said last time. This is where the area where that roundabout is being added in. In the yellow is where the area that's going to be around the roundabout. So for the yellow, these areas are pretty much located for each inlet, which inlet is in charge of. So in the purple is where the inlets are located. In the blue is where the storm sewer system is going to be designed. And in the brown is where the manholes are located. And for the red is my concentration time, which consists of your Q flows. Here are some of the Q flows that I designed for inlet 1 through inlet 4. So pretty much Q flow equation consists of CIA, which C is my runoff coefficient, I being the rain intensity, and A being the areas that each inlet is in charge of. So we designed for a 10-year design flood and a 50-year design flood, but we mostly just focused on designing for the 10-year design flood. And here are some of the cues that I came up with. So for inlet 1, we got 0.33 CFS, inlet 2, 0.52 CFS, inlet 3, 0.4 CFS, and inlet 4, 0.7 CFS. So we designed for 3 main storm sewer pipes, and this pretty much consists of based off what the Q flows we accounted for based off the 10-year design flood, and pretty much the slope of the road and the elevation. From manhole 1 to 2, the pipe that we designed for was 14 inches. From manhole 2 to 3, pipe 2 was 18 inches, and from manhole 3 to 4, pipe was also 18 inches.
So for a life cycle assessment, it is like examining the environmental impacts, addressing a particular product from what they say cradle to grave, which includes the production or the extraction of the product, all the way through construction, product use, end of life, and then potential net benefits being the possibility to recycle that product. For this project, I decided to analyze the life cycle assessment of concrete versus asphalt. So this table describes the stages in which this assessment is broken off into. For this project specifically, I decided to highlight just the first stage, the product stage, and then broken into 3 categories: the raw material supply, the transportation of that supply, and then the manufacturing. So this table shows some of the numbers that I got just examining the number of emissions each process goes through. The first row is showing the hot mix asphalt, again into those 3 categories, and then the number of emissions for each of those categories with a total of the 51.4 kilograms of CO2 equivalency. And then in the second row, it shows the concrete in the same categories. As you can see, the transportation category is significantly higher, and we found that the studies that I saw, or the I looked into, the concrete study took into consideration something called transit mix, which is the mixing of the concrete during transportation, which emits, as you can see, a lot more emissions during that portion, and then that was put into this stage. When in the asphalt study, they didn't take consideration. So in this third row, I factored that out and I got the 5.4, and then totaling that up, that total was easier to compare with the asphalt number that I got. And then to conclude, the concrete is better because it produces less emissions.
I did the life cycle cost analysis comparing asphalt cement concrete to Portland cement concrete to see which one was most cost effective for this design. Asphalt has a design life of 10 to 15 years, and Portland cement concrete has a design life of 40 to 50 years. Our design thickness that we calculated for asphalt was 6 inches, and for Portland cement, it was 8.5 inches. And so the analysis period for this project we did as 20 years, and the design width of the road would be 40 feet, with its length being 1 mile. And these values I used in later calculations. So the materials that I accounted for would be for the asphalt, as well as the different maintenance techniques that I would be using throughout the design life. And I found all of these on the North Dakota Department of Transportation 2023 bid cost estimates. And I converted all of these values to be in dollars per mile. I then used the pavement condition index method. I used the equation on the top to, with the analysis period of 20 years, to calculate, given the year, how the performance of the pavement would be. And if the rating was between 71 to 84, then I would account for maintenance to be done. And if it was 51 through 70, then for a major rehabilitation. And so then I calculated the costs during those years. And for Portland cement, I did a similar procedure with a different equation. since Portland cement has a longer life, I only needed to do to account for one at year 16. So to compare these costs at those years, I decided to make them all into a present worth. And using an interest rate of 4%, I was able to find all those interest rates and find that total present worth. So for asphalt, it was a present worth cost of $935,704. And for Portland cement, it was a cost of $2,995,117. So given these two values, asphalt has a higher present worth, which would be the better option because it's also a third of the price of Portland cement. So our final design, we did go for asphalt of 6 inches with 18 inches of base. For the drainage, we designed for 11 inlets with 3 main storm sewer lines. And our life cycle assessment that concrete production emits less CO2 emissions. However, we decided that the cost was more important because the value of the emissions between asphalt and Portland cement were pretty close. And for the final cost, it would be that $935,704. So some challenges that we faced were creating appropriate deliverables for each team member, given that this was a continuation of last semester's senior design. And drainage systems and emissions were new territory for us. So we collaborated with Apex Engineering as well as Umary professors. Apex Engineering is the current engineer on this project. And we also collaborated our final decisions with each other so we could determine our final design. Are there any questions?
No, I stuck with just the two, just because it's a little easier to find in our pavement textbook. And then it had more, it's broke down a little bit more inside the book as well. So it just kind of made it a little simpler.
There's like different base heights underneath it.
We stuck with 18 because it was just pretty much all clay down there. So it was very poor to build on. So we kind of just stuck with the thicker base.
For the consideration of the load on the road, did you guys consider the current one or like what the city is like planning on how the road toward south?
It's for planning for the future. Yeah, it'd be like it accounted for, I think it's 25 years is what their estimated growth was.
Any last questions? Did you have to take into account all cost in your cost analysis to break in all of that aggregate?
I did not account for them all. That's another thing. That's a good thing to consider.
Great, thank you very much.